if we were to do a motion diagram of an object being thrown up into the air, like that, it goes straight up, comes straight down, it would look something like this, right? It has some initial velocity. So if this was our, if this was y, and we, it would be at, it would start out at the bottom, right? Then it would be up here, right? Maybe 1 second later. Then 1 second later it would be here. Then 1 second later it would be here. Something like that, right? And then it would start to come back down. That would be the way up. And then it would start to come back down. And if I, it would end up here, and then here, and then here. Okay, up and then back down. And if I were to push a car on a track, frictionless track, give it a push and let go of it, and it just moved with constant speed, what would I get in my x direction? Something like that, right? Something moving with constant speed, right? Those, remember the motion diagram, those dots are equal time intervals apart. It's the position of our object at equal time intervals. So, when I throw something through the air, initially it starts out with some initial velocity in both x and y, with both an x and a y component. And 1 second later, it might end up here. And 1 second after that, it might be here. And 1 second after that, it might be up here. 1 second later, it's going to be over here. 1 second later over here. And 1 second later over here. So it's going to follow this, this parabolic path. But what I'm trying to show you is that we can sort of dissociate the two dimensions, x and y, and look at them independently. So if you were to project these dots down onto the x-axis, it's as if it's moving with constant speed in the x-axis because it is moving with constant speed in the x-axis. There's no acceleration in the x direction if there's no air resistance, right? So as our object moves through the air, nothing is pushing on it in the x direction. So whatever velocity in the x direction it started with, that's the velocity in the x direction that it always has. And in the y direction, it starts out with an initial y velocity, but there's acceleration in that direction. But it's as if we just threw it up, straight up into the air, right? We could project these dots onto the y-axis, and we would get the same pattern as if we just threw it straight up into the air with the same initial velocity in the y direction. Okay, so I'm going to throw my projectile up, and it's going to have some initial speed in this direction, and we'll see if it follows that path. You ready? Need more Vy, huh? More Vy? Now I can quit while I'm behind. You could see the pattern though, right? If I could match the initial condition right, then it would follow along those dots, and it would be that parabolic path. In the y direction, it's as if the motion is straight up and down. In the x direction, it's as if it has constant speed in the x direction. Okay? When you have a two-dimensional kinematics problem, What should we do? Throw something off a cliff or something? How should we do it? There's our object, and we'll give it some initial and we want to know where is it going to land, right? It's going to have a path that looks something like this. And we want to know where does it land, right? What's this distance? So the approach here split up the x and the y motion and coordinates. So we'll have, this is like doing two one-dimensional kinematics problems. So we've got our x motion and our y motion. What's the first thing we want to do when we do these problems? Define your origin. Where do you want the origin to be? So this is going to be our origin. And what direction do you want to be positive? X direction, right positive? Right. Okay. That's our plus x direction. How about the y direction? Up. Most people like up as positive. That's our plus y direction. Okay. So we define the origin, define our positive directions. Now we fill in our charts, right? So this is going to be x initial, x final, velocity initial in the x, velocity final in the x, acceleration in the x, and time. And in the y, y initial, y final, v initial in the y, v final in the y, acceleration in the y direction, and time. Here, let's make v initial be 20 meters per second, and theta can be, how about 30 degrees, and h 50 meters. Sound good? So let's start filling in what we know and what we don't know. So what's our initial position? 0 for both x and y, right? Our final x? We don't know. That's what we're solving for, right? That's the goal here. Our final y? Negative 50, right? Because the top of the cliff is 0, up is positive, so we're on the view it as a number line, right? We're on the negative side of the number line, 50 meters. Our initial velocity in the x direction. We've got to break up that the initial velocity was given at some angle. We have to break that up into vectors. I'll draw them in, I'm running out of colors here. How about blue for this one? So that's our v initial x, and then in green here, v initial y, right? So in our x direction, we have positive 20 cosine 30 degrees, and in our y direction, it's also positive 20 sine 30 degrees. You see that? Okay. V final. We know them? No. And we really don't care in this problem. You could find them if you want. We don't know. We don't really care. Acceleration in the x direction? In the x direction? 0, right? There's no acceleration in the x direction for projectile motion problems. And in the y direction? 9.8 meters per second squared in the downward direction, which is negative for us. So if we look at these, we're looking for the distance. Time we don't know, right? Okay, so we're looking for x final. That's what we're trying to find. But we don't have enough information to find x final. It's like sitting down to do a puzzle and one of the pieces is missing. Can't do the puzzle, right? It's no fun. But there's some other information given. And with this information, maybe we can solve for the missing piece of the puzzle and then finish the puzzle, right? So what links these two is the time. Because when the projectile makes it to the bottom of the cliff, it makes it there at the same time in the x direction as it does in the y direction, right? The time is the same. So these two times are the same. And we have enough information given in the y direction where we can solve for t. So we'll use the y motion, solve for time, plug that into the x motion, and then we'll solve for x final. I'm going to use the one that's missing v final, right? So we get a quadratic then right off the bat. So the first thing we're doing is y final is y initial plus v initial in the y direction times t plus 1/2 a y t squared. And you plug in your numbers. What do you get? Minus 50, 0. What was v initial in the y direction? 10. You're going to get two roots. Maybe one of them's negative, one of them's positive. Yeah, one of them's going to be negative, one of them's going to be positive, because you can see that if you had completed this parabola, you'd end up back over here somewhere. And so those are the two points when the object would be at ground level. Right? The equation doesn't know you're standing on the top of a cliff. It just knows that that's the condition you gave it to at t equals 0. So at some negative time, it completes the parabola and says at some negative time, you'd be back at 0 again. But we don't care about that. We just want the positive time. And then plug it into the other side. And once you have it in the other equation, then it's just distance equals rate times time, right? And you can figure out the, or look at your kinematics equations and figure out what x final is.